Okay, so I'm going to do a brief explanation for calculating work required to pull a 200-pound cable up a building, 100-foot tall building. So we're going to measure force in foot-pounds. We're going to do this in a different way than you might think. You might first think, okay, well, what we'll do is we will start pulling from the top, and the cable's going to slowly move up like this till it gets to the top. Yeah, that makes a lot of sense to think about. Now, as far as building an equation to use such that we can calculate the work performed, there's kind of a fun way to do this. And so what we're going to end up with, and I will explain, this is 200 pounds per feet. And this has to do with, alright, were we to take small pieces like this from the top, if this were stuck to the building, take a really small piece, another really small piece, and each one of those move up a distance x. We're just going to call this x. Move up a distance x, take another little piece, move that up a distance x. Let's say each one of these pieces has a length delta x. So delta x length, move that up a distance x, keep going down this cable as if it's something fixed to the wall. And so we're going to go from 0 distance from the top all the way down to 100 distance from the top. A lot different than you'd think we might set this up, but so dx is that idea we often talk about, the limiting process. So this delta x that I'm mentioning is sort of represented by the differential dx in concept. And this 2 refers to the density pounds per feet, and x refers to how far we move a small segment if we were to move a finite size segment. So if that's all you need for explanation, then stop there and do the integration, and there's your answer. But I will go up here and explain in more detail, still pretty brief. Okay, so for simplicity, let's just say we choose some small length. So length delta x for each little piece of cable. So if this were 1 foot, then, alright, we have 1 foot of cable. And let's think of moving this from the center of that piece of cable. And so, given this piece of cable, 1 foot, or we're still going to just say delta x feet from now on. Well, we want to know about force. We want force times distance for work required to move that little piece to the top of the building. And so the force involved is going to be in pounds. Since we're using the US customary system, pounds itself is a unit of force, or a measure of force. So since delta x is the length of the cable, and since the cable is 200 pounds for every 100 feet, then this would be 2 times delta x pounds for this small piece of cable of length delta x. So that is the amount of force acting on this little piece of cable if we were to take this and move this up to the top of the building. So like I'm saying, instead of thinking of this moving upward, we're going to think of this in terms of now just a a straight piece, a straight object, and we're cutting this object up into lengths of delta x. We're grabbing those pieces and moving them to the top separately. So this is the force on each piece. Now the distance that we move is important. That gets us work applied to each piece of cable that we've cut up. And we'll call this x feet, or maybe x star. You could see an index xi star if we're going to say, well, we'll index these by how many pieces we've decided to cut this up into. But we have this little piece of cable right here, maybe it's over here, and we move this up by x feet. Now the next piece of cable is further down, so we move it a further distance, and that's why the star is there to indicate, well, each of these pieces has its own position, and that position is going to be the distance that we move it to get to the top of the building. And so as we go further and further down, as if we're cutting this piece off and moving it up, the distance to move those pieces up becomes greater and greater. And so we don't have a constant for work. We don't have just multiply 100 by force, because it takes a lot less work to move these small pieces to the top as compared to these other pieces. So force is a constant given that we've chosen to cut these pieces up into lengths of delta x each. So force is constant. Distance is always changing. For each piece, there's a greater and greater distance that we must move these little pieces. And so now let's rearrange this so we can get this into the form that we customarily have or typically have: foot pounds. So we've got distance in feet and we've got pounds right here. All we're going to do is take feet, express it here, pounds, express it here, and I keep the colored label just so that we can keep track of what we're doing here. Delta x is the length of the piece of cable. X is the distance of that little piece of cable that we actually end up moving. And 2 happens to be the pounds that we're talking about, so that we've just rearranged everything like this. Alright, so then what's the deal? We have feet here, we also have feet here, and we have pounds. Well, let's not overcomplicate this. Let's just go back to what I was talking about. We're getting really creative here. Rather than taking a force equation, rather than saying, all right, force is 2x somehow, we're generating an equation for overall amount of work acted on a small piece of cable of length delta x, and now we're going to do a limiting process. Supposing we were to just continually take smaller and smaller pieces instead of deciding to define a length of delta x, maybe delta x over 1,000,000, and that's our new quote delta x. Well, that gets closer and closer to the exact work under ideal conditions. No friction, no anything outside of our realm of ideal simplified stuff. Let's say stuff. So that limit, this actually goes to 0, which is impossible to have pieces of 0 distance. But as we approach 0 here, this then can be expressed as our differential dx. And the 2x refers to the distance that each actual finite length piece moves if they are finite pieces. And so as we go out to infinity, the limit of the summation of all these different amounts of work we do on each piece will end up being this integral, where we move from a distance of 0 if we were to have practically 0 if we were to have a very, very, very small piece that has to move almost nowhere to get to the top. And then we continue moving down. We're pretending, like I said, this is what we're doing. We're pretending we're cutting pieces in a downward way rather than slowly moving the cable upward, rather than pulling it upward. And in fact, it could, let me just mention this could be a solid cable. And it's possible that we are cutting this solid cable up like this for some reason, some practical reason. It might not necessarily be a metal cable or anything like that. So there is a real possibility that we do this kind of thing. Anyway, okay, back to this. Distance for each piece, 2x. Small distance, delta x. As delta x goes to infinity, very simplified way of putting it, we end up with this nice equation for work. And, perform the integration, square 100, and you get a 10,000 foot-pounds. And one thing we could do, actually, we could think of foot-pounds as a constant. We could even think of 2 as a constant. We could have taken the 2 outside here. And 1 foot-pound. Take that out so we remember the unit that we're using. It's important to remember that. We perform the integration, and then once we're done, once we get the numeric value, we write the quote constant 1 foot-pound. We express it here rather than in front of here, of course. And yeah, we're done. So I hope that was helpful. I would have liked to do this more thoroughly, but to save everyone time, including myself, because I almost have a life. Okay, we'll edit that last thing out on the second draft of this. Anyway, to save everyone time, what? Oh, there's not going to be a second draft. Yeah, I have too much stuff to do. Anyway, I hope this was helpful, and I will see you in class. Possibly. We get nearly perfect attendance every time, so make it perfect attendance and show up. I will do this better in class than I will in this video. Why are you still listening anyway? You really should be going on to the next thing or doing work. Oh, no pun intended. Also, I forgot to hit stop.